So far, we have examined inelastic collisions, which can be solved using conservation of momentum by itself. That's because for inelastic collisions, some of the energy of the colliding objects is turned into heat as the objects collide and deform. But there's another category of collisions, elastic collisions, in which both momentum and kinetic energy are conserved. And so we must analyze these puzzles with both conservation laws simultaneously. A classic elastic collision is between two objects that bounce off each other without deforming when they collide. For instance, collisions between billiard balls are almost elastic. Consider this example. A 1 kilogram object moves rightward at 6 meters per second. It hits a 3 kilogram object. The collision is elastic. What is the final velocity of each object? In this question, we were told that a ball was initially in motion and it's going to strike a larger ball. After the collision occurs, we want to find out what the velocities of these two balls will be. We don't know what they are, so I can't really put in any arrows. We don't know which direction they're moving in, for that matter. I'm going to call photo 1 the condition of the balls before the collision and photo 2 after the collision. Now, let us put in all the information that we know. One of the balls has a mass of 1 kilogram. Another one has a mass of 3 kilograms. The 1 kilogram ball is moving at 6 meters per second. And we know that they are going to collide. I'm going to put my origin and axes at the point of collision. So rightwards is x, upwards is y, and something similar in photo 1. It's really not necessary, but it's for the sake of consistency. Now, let us apply conservation of momentum to these two situations. Now, conservation of momentum says that the momentum in photo 1 must equal the momentum in photo 2. In the interest of saving space, I'm going to dive into one of the later steps where we just write out conservation of momentum instead of specifically listing out the formula for it beforehand. So applied specifically to this case, the momentum of the 1 kilogram ball in photo 1 plus the momentum of the 3 kilogram ball in photo 1 is equal to the momentum of the 1 kilogram ball in photo 2 plus the momentum of the 3 kilogram ball in photo 2. Again, I'm not going to write out all of these terms one after the other because I don't have the space for it in this question. Instead, I'm going to just write out what are each of the bits of data which go into solving for the momentum, for each momenta. Momentum is equal to mass times velocity. So let's go one by one. The 1 kilogram object in photo 1 has a mass of 1 and a velocity of 6, I hat. Plus, in photo 1, the 3 kilogram object has a mass of 3 and a velocity of 0, which is equal to, in the photo 2, the mass of the 1 kilogram object is still 1 kilogram, but its velocity is something new. We don't know what it is. And for the 3 kilogram object, the mass of this object is still 3 kilograms, but we don't know what its velocity is either. Simplifying all of this, we get 1 times 6i gives us 6i, and 3 times 0 cancels. So 6i hat is equal to the velocity of the 1 kilogram object in photo 2 plus 3 times the velocity of the 3 kilogram object in photo 2. So this is as far as we can go with conservation of momentum. So we have now ended up with one equation with two unknowns. We cannot simplify this any further. That means that we now need to turn to conservation of energy in order to figure out what the velocities would be. So let's take a look at conservation of energy. The kinetic energy of ball 1 in photo 1 plus the kinetic energy of ball 3 in photo 1 is equal to the kinetic energy of ball 1 in photo 2 plus the kinetic energy of ball 3 in photo 2. Now, you'll notice that this isn't the standard way of writing conservation of energy. I've again taken a bit of liberty to save space. In this situation, there is no spring potential energy, there are no springs. There's no gravitational potential energy because nothing changes its height. There's no work in or work out because in an elastic collision, you save all of the energy. None of it is lost through work out, none of it is gained through work in. So the only thing left over is kinetic energy. And each of these terms, each of these balls has its own kinetic energy. So let's go ahead and let us solve for what the kinetic energy is going to be. Like I did over here, I'm going to skip a step and I'm just going to write down how we solve for kinetic energy instead of writing out the full equation. Kinetic energy is 1/2 mv squared. So that would be 1/2 times, for the 1 kilogram in photo 1, that's 1, multiplied by its velocity, 6, squared, plus half, mass of the 3 kilogram is 3, times its velocity, 0, squared, and all of that's equal to 1/2 times the 1 kilogram object, multiplied by its final velocity, which is unknown, plus 1/2 times the 3 kilogram object times the velocity of the 3 kilogram object in photo 2, which is also squared. So now let's simplify all of this. Half times 1 times 6 squared gives us 18, plus this term goes away because that's 0, is equal to half times 1 times velocity of the 1 kilogram in photo 2 squared plus 3/2 times the velocity of the 3 kilogram object in photo 2 squared. Now, to simplify this a little further, I'm going to multiply everything by 2. That gives us 36 is equal to velocity 1 in photo 2 squared plus 3 times the velocity of 3 in photo 2 squared. And that is as simple as we can make this. This is what we get when we solve out conservation of energy on this system. So now we have two equations with two unknowns. Let's go ahead and let's start combining these. This equation can be rewritten as the velocity of the 1 kilogram in photo 2 is equal to 6 I hat minus 3 times the velocity of the 3 kilogram in photo 2. We are now going to substitute this into this equation over here. 36 is equal to V of the 1 kilogram in photo 2 squared, but we already know that that's equal to 6I hat minus 3 V of the 3 kilogram in photo 2. This whole thing gets squared, plus 3 V32, velocity of the 3 kilogram in photo 2, also squared. Now, to multiply this out, we basically write this twice and then do FOIL, like this. 6I hat minus 3 V32 multiplied by 6I hat minus 3 V32 plus 3 V32 squared. So let's do FOIL. 6 times 6 is 36. Outsides, 6 times negative 3 is negative 18. Insides, negative 3 times 6 is another negative 18. Lasts, negative 3 times negative 3 is positive 9. And this whole thing now gets added to 3v32 squared. We can simplify this, obviously. 36 and 36 are there on both sides, so that's going to cancel out. Negative 18 and negative 18 will combine, and we can also combine the v32 squared terms as well. So if I simplify all of this, I end up with 0, as 36 and 36 cancel, equals negative 36 v32 plus 9 plus 3 gives us 12 v32 squared. We're almost done. Now we just need to take this and we are going to rewrite this slightly. I'm going to move the 36 over to the other side. That gives us 12 v32 squared equals 36 v32. I can divide both sides by 12. That'll give us a 3 over here. And I can also divide both sides by v32. So the squared goes away and this v32 goes away. So I end up with v32 is equal to 3 I hat meters per second. So this is the final velocity of the 3 kilogram object in photo 2. And we can easily find the velocity of the 1 kilogram object using this equation back over here. Remember how I said that v12 is equal to 6 I hat minus 3 v32. We know that v32 is 3, so that means that v12 is equal to 6 I hat minus 3 times 3, which works out to negative 3 I hat meters per second. So this is the velocity of the first ball after the collision occurs. The first ball moves leftwards at 3 meters per second, and the 3 kilogram ball moves rightwards at 3 meters per second. So to review how we did this entire question, we started with conservation of momentum and conservation of energy. Conservation of momentum took us part of the way, but we ended up with one equation with 2 unknowns. That can't be solved. Conservation of energy gave us a second relationship between these two variables. So what we next had to do was to take conservation of energy, plug it into, and take this expression for v12 and plug it in for v12 over here, and then through some simplification, we were able to find out that v32 is equal to 3 I hat. And v12 can be solved very by plugging into any of these equations here. You end up with v12 equals negative 3 I hat. So we are able to solve for the two velocities by using conservation of momentum and conservation of energy. Now, let's expand this. What if both objects are moving? Consider this example. A 1 kilogram object moves rightward at 8 meters per second. A 2 kilogram object moves rightward at 4 meters per second. They collide. The collision is elastic. What is the final velocity of each ball? In this question, we were told that one object was headed rightwards at a reasonably high speed, and a second object was also headed rightwards, but at a slower speed, and the two are going to collide with each other. So here's the point of collision. We do not yet know what the velocities of these two objects are going to be afterwards. I'm going to call before the collision photo 1 and after the collision photo 2. The mass of the first object, the one at left, was 1 kilogram. The mass of the second object was 2 kilograms. The velocity of the left object was 8 meters per second. The initial velocity of the second object was 4 meters per second. So, all that being said, let us draw in the origin and axes. We usually set the origin at the point of collision. I'm going to set rightwards as positive and upwards as positive. And there we go. So that is what our setup looks like. Now, let us start applying conservation of momentum. Again, to save space, I'm going to skip a couple of steps here and there. I will say that the momentum of the 1 kilogram object in photo 1 plus the momentum of the 2 kilogram object in photo 1 must be equal to the momentum of the 1 kilogram object in photo 2 plus the momentum of the 2 kilogram object in photo 2. Now let's expand this out. The definition of momentum is mass multiplied by velocity. So let's find that out for each one of these bodies over here. So for the 1 kilogram, mass 1, velocity 8 I hat. Plus, for the second object, mass 2, velocity 4 I hat, is all equal to the mass of the first object, 1, multiplied by the velocity after the collision, which would be v12, plus mass of the second object, 2, times the velocity of the second object, which is v22. Now, 1 times 8 plus 2 times 4, that's going to give us 16 I hat overall. So that's 16 I hat is equal to v12 plus twice v22. So this is our first equation. We cannot simplify this any further. This is the first relationship between the two velocities. Now, what about for conservation of energy? Well, again, we will simplify this a little bit by just looking at the kinetic energies, since there's no potential energies, no springs, no changes of height, and there's no work in or work out because this is an elastic collision. We can say that KE1 before the collision plus KE2 of the second object before the collision is equal to kinetic energy of the first object in photo 2 plus kinetic energy of the second object in photo 2. Now, let us expand these out using the definition of kinetic energy, which is half mv squared. 1/2 times the mass, 1, times velocity, 8, squared, plus 1/2 times 2 times the velocity, 4, squared, is equal to 1/2 times the mass, 1, times the velocity, that would be v1 in photo 2, squared, plus 1/2 times the mass, 2, times the velocity, v2 in photo 2, squared. So, half of 8 squared is 32, and half of 4 squared is 8. But that multiplied by 2 is going to give us 16. So the entire left side works out to 48. 48 equals 1/2 v12 squared plus v22 squared. And we could simplify this still further by multiplying everything by 2. So twice 48 is 96, is equal to v12 squared plus 2 times v22 squared. And this is the simplest way of writing the equation that we get from the conservation of energy. Now, what are we going to do with these? Well, what we can do is we can follow a similar procedure as before, where we isolate V12. So V12 is equal to 16 minus 2V22. And we now take this and we plug it into this equation over here. So 96 is equal to V12, which is 16 minus 2V22 squared plus 2V22 squared. Let's keep going. We have to write this out twice. 96 is equal to 16 minus 2V22 times 16 minus 2V22 plus 2V22 squared. Now we are going to solve this using FOIL. 96 is equal to 16 times 16 is 256. 16 times negative 2V22 would be negative 32. V22. Negative 2 times 16 gives us negative 32 again. Negative 2 times negative 2 gives us positive 4. And all of this gets added to 2V22. So simplifying this entire equation that we have over here, this is going to turn into 4v squared plus 2v squared is going to become 6v22 squared minus 64 v22 plus 256 minus 96 is going to be 160. And all of that is equal to 0. This is a quadratic equation, and I could write out the full quadratic formula in order to solve this out. However, due to space limitations, I won't be able to fit that all on this sheet of paper. So, on the assumption that you guys know how to solve the quadratic formula already, I'm going to use my calculator and solve it for us. So, the value of A is 6, the value of B is negative 64, the value of C is 160. And so we get that the velocity of the 2 kilogram ball is either 4 or 6.67. Now, 4 was the velocity before the collision occurred, so the correct answer must be 6.67. So that would be 6.67 I hat meters per second using the quadratic formula. And so we now are in a position where we can find out what V12 is as well. V12 equals 16 minus 2 times V22. So V12 equals 16 minus 2 times 6.67. So 16 minus 2 times 6.67 gives us 2.66. 2.66 I hat meters per second. So that is the velocity of the first ball, the 1 kilogram ball, after the collision takes place. The 1 kilogram ball is going to travel forwards at 2.66 I hat meters per second, and the 2 kilogram ball is going to travel forwards at 6.67 I hat meters per second. In this video, we explored some basic elastic collisions. Elastic collisions in 2 dimensions are very similar to inelastic collisions in 2 dimensions, provided that only 2 variables are unknown. In the rare case that 3 variables are unknown, elastic collisions require more complicated math to solve. This brings us to the end of momentum, and we are ready to proceed to the topic of rotation.